welcome to this webinar on the Reconnaissance mission in Morocco. Very happy to have our team present their findings, and also very happy to have so many people still coming in. So thank you for the interest in this seminar. And thank you. I mean, also from the SGEB, we are very happy that we were able to send this mission, especially thanks to the initiative and the wonderful organization by Hamza, to which I think I'll pass the mic, so to say. So one more information before we start. During the webinar, you can write your questions in the Q&A chat, and then we will address them after the presentation. So Hamza, thank you.
Yeah, thank you, Pia. Hello, everyone. Welcome to this webinar about the earthquake reconnaissance mission in Morocco that was carried out by members of the Swiss Society for Earthquake Engineering and Structural Dynamics. We make this reconnaissance mission from the 23rd to the 27th of November 2023. So it was a little bit more than 2 months after the earthquake that struck the High Atlas region in Morocco. And in this slide, we can see the contents. So first of all, we will give a brief introduction about the mission. We will present the seismological and site aspects. Next, we will present the post-seismic response with example of damages that we observed in various villages and on different type of structures as well. And finally, we will show some reinforcement measures that were taken in the old city of Marrakech. And I am Hamza Sehaqui, civil engineer, and I had the opportunity to participate to this mission with Afifa Imtiaz, Eric Latian, Gustavo Cortés, Meriton Beqiraj, Mylène Devaux, Savvas Saloustros, and Joanzu. Before beginning, we wanted to mention that this mission would not have been possible without the support of the Rebuild program, who did really an amazing organization. So the Rebuild program is an initiative that is set by the OCP, which is a Moroccan industrial group, to participate to the post-seismic management in the affected areas. So Mr. Hassan Qaddouri, Professor Khalid Amrouche, Mr. Abdeslam Yahyawi, and Mr. Yusuf Al-Bouhali hosted us with really great hospitality. And in the next slide, yeah, so the first day they hosted us at this beautiful university, which is the UMCSP of Ben Guerir, where we had conference that were organized, and we discussed some scientific issues to understand better the impact of the High Atlas earthquake. So these discussions were mainly focusing on the seismological and geological context, and on also on the post-seismic management of the event. Then during the following 4 days, we had the opportunity to visit villages that were badly affected by the earthquake within a distance mainly between 10 to 40 kilometers from the epicenter. So the second day we visit Tufsirin, Al Baraka, Imgdal, Talat Yaqub, and Tiqiyut. The third day we went to Amzmiz and Tafghart. And the last 2 days, we observed the damages and some also reinforcement measures in the old city of Marrakech. Just as a reminder, the earthquake struck Morocco on the 8th of September 2023. It was about, the epicenter was about 70 kilometers southwest of Marrakech with a magnitude of around 7. So it was so strong that it was felt all over the country. And it happens at 10 o'clock in the evening when a majority of people were at home, some already sleeping. So there were more than 2,900 deaths and 5,600 injuries. And also the localization of the epicenter made the rescue a bit difficult since it was in a region where the access was really difficult due to multiple landslides over several kilometers. And for information, yeah, Morocco have seismic codes, actually two. Le règlement de construction parasismique, RPS, which concern mainly concrete diaphragms and mixed concrete masonry walls. More precisely, concrete frame with masonry fillings, yeah. And the other code is the Règlement parasismique des constructions en terre, which concern adobe and earthen structures. Yeah, and here these are the most common constructions that we met in the High Atlas region. My colleagues will introduce more in details these structures, but yeah, before that, Afifa from the Swiss Seismological Service at ETH Zurich will present the seismological and site aspects.
Thank you, Hamza, and hello, everyone. So let's start with the observed ground shaking intensity from the Haouz earthquake. On the left picture, we see that close to the epicentral area, for example, in Amizmiz, intensity 8, meaning severe shaking with heavy damages, was observed. In Marrakech, intensity is up to 6, meaning middle to strong tremor, so it's light damage was observed. On the right picture in gray circles, we see the locations of the aftershock with magnitude above 4. The main shock was followed by a magnitude 4.9 aftershock just after 20 minutes, which also contributed to damage. Next is the PGV distribution. So USGS compared the observed ground motions shown by circles and triangles on the left figure with the ones from ground motion prediction equations for soil, shown in purple. We see that the observations generally exceeded the prediction. The ground motion reached up to 0.78 G at a seismic station 30 kilometers away from the epicenter and was felt up to 0.5 G in Marrakech. On the right, we see that the sites we visited fall within 0.2 to 0.5 G contours. Next, I show some recordings of the event. On the left, I show some stations from European networks. The closest station, Tiwin, is about 100 kilometers away from the epicenter and recorded a PGV of 1.5 centimeter per second. The 4.9 aftershock also appears on the seismograms. And as we go northwards from Morocco through Spain until Salève near Geneva, we can distinguish PES and surface wave arrival phases more clearly. Next slide shows the response spectra comparison. On the left, we have the zoning map from the National Seismic Standard of Morocco. The epicentral area and the sites we visited fall in the moderate seismic zones 3 and 4. On the right, I compare the response spectra estimated from the seismic stations that we have recordings for with the design spectra of different soil types of zone 2. The closest station, Tiwin, exhibits a spectral acceleration peak of 0.16 G at 0.14 second, which remains below the code spectra. Next, we show the seismicity and seismotectonics network at play. Morocco is located at the boundary of the African and Eurasian tectonic plates, which are converging at 4 to 6 millimeters per year. This area is seismically active and has resulted in several damaging earthquakes. The map from Shaloni et al. 2024 shows instrumental earthquakes, major seismic events, and major tectonic lineaments of the area. The Al Haouz event occurred in the west part of the High Atlas Mountains, about 550 kilometers south of the plate boundary. In the High Atlas, the seismicity is low, but it has produced the 1960 magnitude 5.8 Agadir earthquake, which destroyed the city and was the strongest seismic event until 2023. Several active reverse faults exist there, but the deformation rate is less than 1 millimeter per year. In a reverse fault, the fault motion is caused by compressional forces, which results in crustal shortening, that is elevation of terrains by the thrusting of one block of crust over another. So the Atlas chain may take longer, but it seems to be able to generate a large magnitude earthquake. The smaller boxes on the right shows the main shock, the aftershocks, the moment tensor, and the surface projection of slip distribution. And we see that this event is an interplate earthquake that occurred on an oblique reverse fault with north-south compression. As no surface faulting was observed, the exact fault mechanism is still not well understood. Next. So why was the Haouz event so deadly? Multiple factors have contributed. The first was magnitude. At 6.8, the earthquake wasn't huge, but it was unusually large for Morocco. A further complication was introduced by the nature of source complexity. The damaged villages were located within the close proximity of the source, and buildings were not earthquake resistant. So based solely on our visual inspection, without analyzing any seismological or geophysical data, we try to examine if side effects could also be important in amplifying ground motions. So next we go to the geology. The area we visited falls into the Haouz Basin, which is formed of tectonic sedimentation with tertiary and quaternary formations resulting from the erosion of the high Atlas chain. It consists of young and alluvial deposits, which makes it susceptible to complex side effects from a combination of topographic and basin effects. So next, we have a look at the most damaged villages. Especially, we can see that the villages like Amizmiz, Talat and Yaqub, Tushrin, and especially Tafgakte are located at the mountain foot and mountain fringe areas where the greatest concentrations of damage occurred. We know that the topography influences ground motion and in general increases the amplitude of shaking at ridges and could also impact surrounding low-lying areas. So next we go to the area we visited in Amizmiz. From the satellite image after the event, we can see relatively more damage on the right side of the street marked by the red zone. And in the next slide, we try to we try to see the state of the buildings on left and right side of the street. The apparently undamaged looking buildings on the left might be relatively new and may have sustained internal damage that we haven't inspected, while the buildings on the right side are located on a mild slope. So we ask ourselves if site has contributed to the ground motion amplification or resonance in this part. Then we go to the before and after picture of damage in Talat and Yaqub. We can see rows of buildings constructed on the slope. The area in red rectangle is zoomed in the next slide. So we have observed ground failures and long cracks near the buildings on the slope. Then we go to the next village, Tafgakt, which was completely leveled by the earthquake. It's located on slopes right at the foot of the mountain. The topsoil looked quite loose. Again, we ask ourselves if some complex side effects or resonance effects have also contributed to the amplification of ground motion here. And then next we go to rock hazards. severe rock falls have been caused by this event. The fallen rocks were already cleared by the time of our visit. However, we observed some of the debris near steep exposed slopes, which seem highly susceptible to ground shaking generated by the likes of the Haouz event. So that's all from me. Thank you all. And next, my colleague Gustavo Cortés will present the context and disaster response aspects from our mission observations.
Hi, everyone. Thank you, Afifa. Our mission was an opportunity to learn from observations, as you will hear from some other of our colleagues, but also to test our Swiss building assessment form, including a newly developed digital platform, which basically lets you use your smartphone or a tablet. But let me start by briefly discussing the seismic response and disaster management cycle. The figure that you see here, which was adapted from the Swiss Federal Office for Civil Protection, shows a diagram that summarizes the phases that you typically encounter after an earthquake or any other natural disaster. Please note that although disaster response is different, the principles shown in the figure are quite typical. The acute phase, which happens right after the event, includes search and rescue and takes place, like I just said, right after the event, those first few days. In this, suddenly people are basically helping each other in a spontaneous way. But as days go on, then there's a more organized help that normally takes place, and that's where the government starts to help other non-governmental organizations as well support. And people in general, they need healthcare support, they need drinking water, food, shelter, hygiene items, etc. So I already mentioned the search and rescue, which takes place normally in days after, but then there's also this seismic evaluation that needs to take place, and that's where people have been displaced and they have to ask themselves, can we go back to our house or should we not go back into the house? Is it safe to be used? This response continues with the recovery, reconstruction phase, and this may take months or very likely in most situations, depending on the magnitude of the event, years. Lastly, but not least, let me just say that preparedness that you see on the left, it's quite important as well. This phase includes not only response planning, like a lot of the planning that it's, a lot of things have to be planned ahead of time, but also it means disaster risk reduction and what things can we do now to try and reduce the risk for when an event happens. If we go to our next slide, please. Okay, so in the case of the magnitude 6.8 earthquake in Morocco, by the time we arrived, it was nearly 3 months after the earthquake, and search and rescue operations had already taken place. Roads had been cleared, at least all the roads that we saw had been cleared. And as you see on the left picture, you can imagine it's quite critical to clear those roads as quickly as possible so that we can access people who are in those more remote locations that in this case were close to the epicenter, and that's where most of the damage or the greatest damage took place. On the right side picture, we see emergency shelter in the Haouz region. And again, this is very critical. People who have lost their place, their house, then they need a place to stay. And in this case, we took a picture showing some of the examples. Next slide, please. As we got closer to the epicenter, we observed that there was still some heavy machinery being used to clear, in this example, a plot of land from some of the houses that had collapsed, some of the buildings that had collapsed. On the right side, it was interesting for me to see as well that, like I said at the beginning, many phases of this cycle kind of merged together. On one side, you had people clearing the plot. On the other side, you have people already trying to recycle some of the pieces that they could recycle, they could reuse, and starting to pour concrete and start some kind of new house. If we go to the next slide, please. At the same time, and this normally happens as soon as possible after some of the spontaneous help takes place, we also observe emergency measures. You have a mosque that have been stabilized with shores to probably prevent any further or any out of plane failure. But if you look a bit closer, it also had been wrapped around with ties, probably to protect the towers. On the right, I have a couple pictures showing some examples. As we went to the old Medina, some of those small roads, small streets had been protected. In that case, had been shored some of the buildings to protect them, and also to protect people as they pass under, because that, you know, life has to continue. If we go to the next slide, please. Can we go to, well, thanks. Okay, so now, once again, our team's mission was to learn from observations, but we also wanted to test the Swiss building assessment form, and including the digital platform that you see on the right picture as well. The aim of this Swiss assessment form is to determine whether a building can be used safely, to estimate the extent of damage, and to determine whether urgent measures, such as the shoring that I showed previously, are needed. Please, next slide. Next slide, please. Okay. Our assessment form was based on the Italian assessment form that you see in the middle. It's based on that assessment form because it has been proven to work really well with the vast experience from the Italian, but it was adapted, of course, to the Swiss context. On the right side, I also show the ATC, the Applied Technology Council 20 evaluation form. They have a rapid version and a detailed version, which has 2 pages. Next slide, please. So we actually did a few evaluations on this presentation. I'm not going to go in detail through those presentations, but those will be on the report. However, let me just really briefly present the main sections of this assessment form. If you look at the 2 pictures on the left, I think it's very clear that there's a lot of damage on those buildings. That they've been severely damaged, partial and complete collapse on the bottom left picture. So we wouldn't bother about assessing those. That's very clear. We wouldn't get any even close to those because that can be dangerous. However, the form, it's really mainly for those buildings like the one you see on the right, which from looking from the outside, you don't really see as much damage. But as we went inside, that's where, if we go to the next slide, you'll see the significant damage that took place in that same house that from the outside, otherwise you wouldn't tell that it was that damage. So we use the assessment to evaluate this building. Like I said, it's more on the report, but again, let me go briefly through some of the main sections. We, on the left top, basically we have to have the information about the building so we can go back to the building and we are able to identify the building. On the bottom part, then we normally have to record number of floors, average height of the floor, the surface, year of construction, if we can know that, and then what's the use and how many people live in that house. Please go next. And this part perhaps more interesting for the engineers between us here. We look at the lateral force resistance system here. We identify that. That's the sort of like the top left portion of the table. But then we also look at whether we have a flexible diaphragm or a rigid diaphragm. We also record what kind of materials were used. Is it masonry, reinforced concrete, and so on? And if there's any vulnerability, then we want to make sure that we capture those, such as a short column and so on. Next slide. The next part that I like to briefly show is that we also try to estimate the level of damage. And for that, we use the European microseismic scale that goes from grade 1, which is negligible, to slight damage, all the way to grades 4 and 5, which is very heavy or complete destruction. Next slide, please. Once we have gathered all of the information, then we again, I'm not showing all the sections, okay? But with this table here, it's sort of a summary in which which allows us then to determine whether the building can be used, that's the green, whether it should not be used whatsoever, that's the red. And then if it's somewhere in between, that's the yellow. That means that there are some immediate measures that need to be taken before anyone can use it, or if we couldn't determine as engineers in this basic assessment whether it can be used or not. So let me finish by this last sentence here. The question that we posed to the engineers in charge of the assessment is this: will the occupants be safe if an aftershock of similar intensity occurs in the vicinity of the building being assessed? Thank you very much. Now I pass it on to Meriton, my colleague, who will talk about the reinforced concrete and confined masonry observations.
Okay, thank you, Gustavo, for your presentation. So now I'm going to add a few comments on reinforced concrete and confined masonry buildings. So first of all, before we move on, just wanted to point out that we did see near Marrakech essentially some RC frame buildings and RC frames with shear walls, which are modern type of constructions, but we didn't focus on these ones, and we focused more on the existing buildings in the areas closer to the epicenter. So what I will do first is describe the quite common typology of structure, and then discuss some damages that we could observe. So on the bottom right picture, we see a very common type of building. So it's made of columns and beams in reinforced concrete with infills or walls made of concrete blocks. And as we can see here, bottom left and middle, we had actually the opportunity to go and visit a factory where these blocks were being produced. So what we did see is that they were manually pressed and then air dried. And it is very likely that these blocks are not intended for load-bearing structures. So as you can see, there are hollow core concrete blocks. Now moving forward to describe the floor system. This was also a very common type of floor system. So they use mainly these kind of beams, so precast beams, reinforced concrete beams. And on top of that, they use concrete blocks to form, as we can see on the top right picture, some floor systems. Usually on top of these elements, there was also an overlay of unreinforced concrete, which was connected mainly only with the surface roughness of the beams, as we can see. And then the floor is connected to ring beams, to ring beams and columns. So the typology I described there was very, very common, and we could see that in many buildings, buildings that could be also 4 or 5 stories. So let's start here with the first case study, which appears to be more of a confined masonry type, because in this kind of buildings and typology, the big question was always, in this case, and those cases, was if it behaved like confined masonry or rather as standard reinforced concrete frames. This first example was in Tlatenyacu, so quite close to the epicenter, and we can assume that it behaved as confined masonry mainly because we can identify a compression strut in the middle picture in the wall. So yeah, we can assume it was confined masonry. However, we can also observe that the principles of confined masonry are not really here. So, for instance, the concrete elements are not really suited for load-bearing walls. Around the columns, we do not see vertical elements, and also the interlocking between the walls and the tie columns is not really present, even though likely the columns were casted before the walls. So at the end, what we see, what you can observe as failure mechanisms are on the top, well, top left and right bottom, some shear failure mechanisms of the tie column. So mainly due to lack or insufficient number of stirrups, but also we can observe, especially on the right picture, lap splices. And then moving forward to the next one. Actually, this one is very close to the previous one. It's right next to it, and looked similar at first glance. However, we identified this one as behaved more as an RC frame because the main reason for concluding to that is the fact that on this facade, it appears that the infill walls fell out of plane. We could also observe that in a way on the left picture. So in terms of failure mechanism, what we observe here is a little different from the previous one. The amount of stirrups looks to be greater than the previous one. However, we do also see some lap splices and local buckling of the rebar, as well with concrete spalling. So these two cases were really representative of many damages we could observe in these, especially in Talatniaku, but also in many other villages. Here, just something I wanted to point out. This is actually the next, right across from the same building I just presented, I just introduced to you. And what it shows is an out-of-plane failure of this infill wall, which was exacerbated by the earth pressure. So this is specifically something interesting. It was interesting because of the fact that the building was on slope. Now to conclude, I wanted also to mention that so we discussed this kind of failure mechanisms, but we could also observe very heavy structural damage, especially this is in the center of Talatniaku. And especially some soft story mechanisms at ground level for these kind of structures made of reinforced concrete and also confined masonry. So those were the observations that I could make for this type of buildings. And now moving forward, I will hand over to Savvas, who will introduce you to stone and earthen buildings. Thanks.
Thanks a lot, Meriton. Hello, everyone. We're starting with vernacular stone masonry buildings. And in this slide, we summarize the structural characteristics of those vernacular structures. This presented in the visited areas 1 to 2 stories. The floor system was made with vernacular flexible floors that we are going to look into in detail in the next slide. And in general, we can say that these buildings were lacking seismic design characteristics, such as robust wall-to-wall connections, wall-to-floor connections, or regular distribution of openings. As we can see in the figure in the middle at the bottom, we also observed in many cases structural variations or transformations that these structures have experienced during their lifetime, with the addition of modern floors from reinforced concrete elements or beam and block floors, as Meriton presented previously, as well as the addition of vertical reinforced concrete elements like reinforced concrete columns and horizontal ones like tie beams. On the right figure, we see an intervention which corresponds to vertical extensions using modern materials such as reinforced concrete and block masonry, which was really common in rural areas like the city of Amismis. And here we can see in detail the traditional floor system that is used in the visited areas, both for stone and earthen structures. On the right is the scheme of this floor system as presented in the Moroccan code for earthen and stone masonry structures. As you can see, starting from the bottom of the floor and moving towards the top, the first element are these rounded timber joists, which extend in most of the cases through the whole thickness of the wall. The only way that they are connected with the walls are through friction supports, so they are simply supported by them. And on top of them, in very few cases, we observed also the use of timber joists with smaller diameter orthogonally to the main ones. But as I said, this was in very few cases. On top of those, on the main beams, there is a wooden mesh, which actually covers the open area and provides the support of a thick layer of soil material or a combination of thinner layers of soil material. As we can see, the code, this is typically between 15 and 30 centimeters wide. And the finishing of this floor system is made with diverse materials like stone tiles or earthen plaster. In modern variations, we also observed the use of cement plaster and as well the introduction of plastic sheets for waterproofing. In here, we present the material characteristics of stone masonry structures. In general, rubble stone masonry is used with undressed irregular stones. Mortar joints are thick, using earthen material as infill. Walls are made from multiple leaves, as you can see in the figure on the right. And in general, we have an absence of through stones, so there is no connection between the wall leaves. In the two figures on the bottom, we see two extreme cases of stone masonry typologies that we observed. On the left is the lowest quality with rounded river stones with smooth surfaces resulting in thick mortar joints, while on the right, in very few cases, we observe this masonry typology with rectangular units and thin mortar joints. Moving now to the damage typologies and starting with in-plane damage. Here we see the case of two adjacent buildings in the old city of Mys, which present a flexural cracking with horizontal cracks at the top and bottom of the piers of the top floor. This corresponds to a typical damage typology of a weak pier, strong spandrel configuration. Actually, these buildings were among the few that were still in use in the old city of Mys, and which means that they perform much better compared to the neighboring ones. And we can attribute that to the regular distribution of openings, as well as the better quality of masonry, as we could observe it from some local loss of plaster. Another typical in-plane damage in the city of Mys was shear cracking at the ground floor of stone masonry buildings, which actually have experienced vertical extensions with modern materials, as you can see in these two images. And this damage typology was the result of a higher normal load coming from the vertical extensions to the ground floors and made from stone masonry. Moving now to out-of-plane damage, one of the most typical damage typologies that we observed in several structures was the collapse of one of the external wall leaves. And this is attributed to the masonry typology, the lack of through stone, as I said. As we can see in these cases, also the presence of reinforced concrete floors could influence this damage typology, as it could result in a non-uniform distribution of the normal forces, the normal stresses, through the thickness of the wall, increasing the vulnerability of the wall leaf that remains unloaded. Also, in cases where we had transformations or alterations using reinforced concrete floors, as in the cases that we present here, we could also observe collapse of entire walls, as well as collapse of parts of the floors. This damage typology manifests that there's a poor connection between modern floors, ring beams, and existing masonry. Also, it can be attributed to the low masonry quality, but actually it can be a combination of the two of them. Here we see the case of transformations using also vertical elements, reinforced concrete elements. And in those cases, we observed the collapse, the partial or complete collapse of the perimeter stone masonry walls. However, compared to what we saw in the previous slide, we didn't observe the collapse of the floor system. and of the modern floor system. And this manifests that the vertical loads from the floor are taken by the vertical reinforced concrete elements, leaving the stone masonry walls unloaded from the floor levers, which actually increases their out-of-plane seismic vulnerability. And in the last two slides concerning stone masonry buildings, we emphasize the importance of masonry quality as we perceive it on site. Here in this slide, we see the image that we actually observed for stone masonry structures constructed using rounded stones with smooth surface. This masonry typology has poor interlocking and also low frictional strength, which actually resulted in complete disintegration of walls during the earthquake loading. And as you can see on the right, the addition of modern floors would not improve, even if it could worsen the behavior of this type of buildings. On the other hand, these two images present two buildings in the villages of Tikiute and Tafakakte, which survived the earthquake with damage, but minor damage. And also it should be said that these two villages were completely leveled by the earthquake. So a common structural characteristic that could improve the behavior of these two structures is the presence of rectangular units and the thin mortar joints. We were not able to visit these buildings in the interior in order to have an idea of the floor systems that it was used, while it seems that in the right side, at least, there is a modern floor. Moving now to earthen buildings, this slide summarizes again the structural characteristics of these structures. Vernacular earthen structures have also 1 to 2 stories. The floor system is the same as the one that we saw for stone masonry structures. And typical of earthen structures is the construction of part of the ground floor, as we can see in these two images, or the complete ground floor in stone masonry. And this is in order to protect earthen materials from the rising moisture from the ground. Again, as in stone masonry structures, vernacular buildings, they lack seismic design characteristics, as also described in the Moroccan code for earthen structures, which means they lack robust wall-to-wall connections, wall-to-floor connections, and a regular distribution of openings. The construction techniques using earth that we observed on site was rammed earth walls, as we can see on the left, and adobe masonry walls, as we can see in the image on the middle. Adobe masonry walls use mortar made from earthen material, but in this case, on this village of Tufsirin, we also observed the embedment of flat stones within the mortar joints, as you can see in these two images. In the same village also, it was really common to observe the combination of these two materials, or more than two. In fact, stone masonry was also quite common, combined with adobe and rammed earth walls. Moving now to the damage typologies, and starting with in-plane damage, here we see the case of two buildings, one in Imtal that my colleague Mylène will present later in more detail, and one in Talat and Yaqub, where we observed shear cracking in short and wide walls, mostly between openings. And a common characteristic of rammed earth buildings was the separation of rammed earth blocks at construction joints. So this proved to be a point of vulnerability in rammed earth buildings. Moving to out-of-plane damage, one of the most typical damage typology was vertical cracking and separation of orthogonal walls. This is attributed to the low strength of adobe and rammed earth, but also, as I said before, to the lack of connection between orthogonal walls and the presence of construction joints that we can see on the right, which actually facilitated the involvement of this damage typology. And actually on the right image, we can see a singular case where we could observe the presence of a timber element providing a level, some connection between orthogonal walls in a rammed earth building. Apart from this lack of interlocking, another factor that has contributed to the wall overturning and collapse of many earthen and stone masonry buildings is the type of floor used. One-way floors, they leave one part of the two sides of the rooms unloaded. So the walls that they were unloaded, and typically facades, they didn't have the stabilized normal force from the floors, and were more susceptible to out-of-plane failure, as we can see in the two images in the bottom left and in the middle. And finally, on the right side, we see the collapse of a corner building in a building aggregate, which actually demonstrate all the structural vulnerabilities of these aggregates, the connection between different materials, the lack of connection between orthogonal walls, as well as the vulnerability of the floor system. We see that the floor beams completely slipped out of their position in the first floor. And with this, we close this part and we move to the next part related with the structurally transformed and historical buildings by my colleague Mylène Devaux.
Thank you very much, Savvas, and hello, everyone. So during our post-seismic reconnaissance mission, we have recorded that many of the observed buildings had been once or several times transformed, I mean, for example, raised or extended. This fact has been already highlighted by my colleague Savvas, just with his presentation before mine, who has shown several cases of natural stone masonry buildings or adobe buildings that have been transformed with reinforced concrete elements, for example, RC frames and or kind of slabs, reinforced concrete slabs. So to keep on with this topic, I would like to present a few other cases of conversion that are more or less representative of what we saw on site. Both situations you can see on this slide involve buildings that were initially built in natural stone masonry or with ramped earth blocks. The building you can see on the left was converted with reinforced concrete elements, kind of, maybe you can show the next slide. Thank you. Reinforced or reinforced with reinforced concrete frames with masonry infills, for instance, or confined masonry. It's always quite difficult to identify if it's confined or masonry infills. And on the other two pictures, you can see the other building on the right, which was converted with, so on one step with natural masonry, stone masonry. So you can see quite in the middle of the building on the height, so with about 1 meter high, and on the top of it, on one step, another step of conversion. So it was converted with reinforced concrete elements with masonry infills. What's interesting here is that this mix of materials, of course, if they are not properly connected to each other, inevitably generates areas of weakness at the interface. Here, the interfaces are highlighted with continuous black lines for the visible interface and with black dashed lines for assumed interface. So as a matter of fact, the behavior under seismic actions of such kind of buildings is strongly impacted by these areas of weakness, as we can see on both pictures here, on the three pictures here, with a cracking pattern due to the seismic behavior of buildings. I also would like to present two other situations of buildings on the next slide, whose structure is composed of different types of materials. So for example, in the picture on the left, and also on the one which is in the middle of the slide, we can see a building whose structure combines natural stone masonry on the ground level and adobe masonry on the first floor level, and also heavy horizontal elements that look like RC slabs or maybe just reinforced concrete floors. They are really heavy floors, and they were most certainly built as a part of a conversion, because we can also see more other traditional floors in this building. It's maybe a little bit more difficult to see, but we can observe them. So it's why we can assume that this building was quite highly converted. So once again, the observed damage show that the areas where the materials change, which I've called interfaces, correspond to areas of weakness and may highly contribute to the ruin mechanism that have been set in motion here. Kind of, as a matter of fact, it is highly, in this case, likely that the upper part of the wall collapsed according to an out-of-plane mechanism whose base surface corresponds to the interface between two types of masonry, in this case between stone masonry and also adobe masonry. In the case of the rear of the building, which is on the right with the picture, we can see, among others, that that there are two layers within the wall thickness. We can see with no apparent connection between them. Thank you. Once again, this must have had a major influence on the out-of-plane vulnerability of this wall. Both buildings are located in the Medina of Marrakech, and this allows me to make the link with the following slides, which deal with historical buildings. So on this slide, you can see horizontal shoring that has been put in place mainly to prevent out-of-plane movement of the masonry walls of these vernacular buildings. This type of ring mechanism is highly dependent, as you know, on the quality of connection between perpendicular walls. And on the picture, we can see that the brickwork ties are not of excellent quality, I mean at the corners, because the crack also at the corner is almost vertical and seems not to indicate brickwork ties of very good quality. Now, regarding other historical buildings than vernacular ones, for instance, sacred buildings like mosque, we observe that most of the minarets had either suffered very serious damage or had simply collapsed, and also that the rest of the mosque structure showed significant damage. There is no point in showing rubbles, but there is a point in showing buildings with light to moderate damage. And in order to illustrate this type of damage, light to moderate damage to mosque, I have chosen to present the cases of the Koutoubia Mosque and Kasbah Mosque in Marrakech. In the case of the Koutoubia Mosque, we can see that the minaret, which is quite high, something like 80 meters high for a square section, something like 10 meters long, is still standing and shows very light damage that are visible from the outside, actually from the ground where we were. Unfortunately, the pinnacle, on the other hand, had suffered serious damage, which is why we can see a kind of vaulting structure put in place after the earthquake in order to stabilize the structure. There are also shoring placed all along the outer walls of the mosque in order to stabilize them against horizontal movement. We can find similar features in the Kasbah mosque, where the pinnacle of the minaret was also damaged and then temporarily reinforced with a form of shoring, a kind of vaulting. In the case of the Kasbah mosque, the final element of the mosque internal arcades have been temporarily stabilized, as you can see on the picture on the right side of the slide. Regarding the minarets, the only difference with the Koutoubia Mosque is that there is a crack in the upper part of the minaret, which you can see in the middle of the slide, thank you. This crack is very probably due to the earthquake because it cannot be seen on pictures that were taken before the earthquake. Eventually, at last comment, I would like to add that there were no visible cracks at the interface between the minaret and the rest of the mosque structure, which was, for me at least, quite surprising because both structure, I mean minaret and the rest of the mosque must have had different behavior under seismic action. So it's quite surprising not to find any crack at the interface between both part of the structure. So this is my last slide. I thank you very much for me. And it's time to move to the global conclusion, and I give back the word to Hamza Sehaqui.
Thank you, Mylène. So we are arriving to the end of this presentation. Before finishing, we wanted to thank the people from villages that who welcomed us with really great kindness. in each village, and despite the sad event, we were hosted with great hospitality. So we would like to thank also our president, Pia, and all the members of the SGEB that allowed us to do this mission. We thank all the people that helped us to carry in general this mission. And for your information, reports will come out soon on the SGEB website. And in the next slide, I just wanted you to thank you again for your attention. And if you have any question, we would be happy to answer them.
Thank you very much, Hamza, and everyone actually for the really interesting presentation. So for the questions, we've seen that there are some questions in the chat. I think the questions actually have already been answered, but maybe just for everyone who didn't see that, I think, Eric, you answered a few about the reinforced concrete construction. Maybe I can let you take up the questions and the answers, give a quick summary for everyone who hasn't seen the chat.
Yes, thank you, Pia. Yeah, there are both of types, confined masonry and concrete hollow blocks with a concrete frame. And about the diameter and the reinforcements of the tie columns, the distance between the stirrups is about 20 centimeters. And we have no information about the characteristics of the materials, but generally poor quality. Yeah.
Okay, thank you. Then there is one more about so there's one more about the Swiss evaluation form. I mean, maybe Gustavo, do you want to just quickly take that up again?
Hi, sure, yeah. So the question was, can you tell us that you then adapt the Swiss evaluation form to the specific features of the Moroccan construction systems? The response was, no, we did not adapt the Swiss evaluation form. The idea was really mainly to test it. We also had a Swiss version, a digital version that we were testing as well. As you may or may not know, we have 3-4 languages in Switzerland, but we were testing really mainly French and English as well as part of what we were doing and collecting feedback. But also, so it wasn't 100% applicable, but it was still a very insightful exercise for us. Mm-hmm.
Okay, thank you. And then one more about the adobe structures and earthen buildings. Savvas, do you want to take that up?
Yes, the question was from Naida Demowitz, where if there were a lot of adobe structures in the visited areas. Well, in fact, in 2 of them and further from the epicenter, so in Marrakech and in Tufsirin, which were around 40 kilometers and 50 kilometers away from the epicenter. When we were visiting villages that were closer to the epicenter, most of the earthen structures were rammed earth buildings.
Okay, thank you. So Mylène, I see you're typing, but maybe do you want to take up the question about the minarets? So there's one question by about the mosque minarets, what the type of material was and they were made of, and maybe you can answer that directly.
So with pleasure. So as far as I know, I think that the materials is masonry, stone masonry, or brick masonry. Brick masonry simply, but plain brick masonry.
Okay. Then we have one more. So there's one great presentation. 2 questions. In case of hybrid constructions of earth, say earthen buildings with reinforced ties, I expect larger damage because of the non-homogeneous construction, but the level of damage was not so high. Why? And then, yeah, maybe we take that. Yeah. Is the question clear, or should I repeat the question? Or
maybe I can take that.
yeah.
I think the question refers to the building that was presented by Mylène. I don't know if Mylène wants also to add a comment. Because not we in case of earthen buildings, there were transformations, but we didn't see so many of them. For instance, this building was the singular case that we saw a vertical extension with reinforced concrete elements in block masonry, but we didn't observe the presence of tiles at the floor level. So we don't really know what is the level of connection between the vertical extension and the existing building from the original building from land earth. So it is difficult to generalize looking at only one case from this building, because actually in the rural areas that we visited, earthen structures did not undergo so many transformations. It was mostly stone masonry structures that had this type of interventions. I don't know if you want to add something, Mylène, to that.
No, I think it was really exhaustive. Thank you very much, Savvas.
Okay, and then there's a question that I think is a bit related. So in the last slide, the high earthen minaret had less damage than expected. What was the reason? Or maybe, I mean, had less damage than expected is a question already. Did it have less damage than expected? Does someone want to take up? I don't know, Mylène, Savvas, one of you maybe, or?
Regarding the minarets, so actually many minarets that we have observed during the mission was really seriously damaged, and even many of them there was nothing left, just because it was so seriously damaged. And the idea here was just to show minarets that was still standing, and just also to give an idea, to present a kind of light damage that can suffer this kind of structure. And they are lucky. So in Marrakech, both minarets, I mean, for the Koutoubia Mosque and also Kasbah Mosque, were not too seriously damaged. So at least regarding visible damage, but it was not the case of another minaret which was close to the place Jimalna. Excuse me for the pronunciation, bad pronunciation, because it just fell down. And maybe it was very. It could be interesting to maybe to compare or to discuss this point with the response spectra of this area, because they are really high. Then we can assume that their behavior, or they behave quite they are quite flexible regarding seismic action. That may be why they are not so severely damaged. But we have to analyze it more thoroughly, I would say.
Thank you. Yeah, I think, Savvas, you're already answering the mortar questions, right? So
yes. So regarding, maybe we just say that live here. It was a question about the mortar, but for the minaret, no, I was thinking about the mortar, about the general mortar in the rural areas was always earthen mortar. In minaret, maybe Mylène wants to answer this.
I think it could be earthen mortar, because both minarets, I mean Koutoubia and Kasbah minarets, were built during the 12th century, if I remember well. Of course, they were transformed, or they have been transformed since the 12th century, but we can assume that the main part of the masonry were composed of earthen mortar. Yeah.
Then, thank you. So then I think we have two kind of related questions. So the question was if there are clear differences in the performance of pre-code and modern buildings, and specifically if how the modern buildings behave. Eric, do you want to answer that?
Yes, the two buildings shown with concrete frame and confined masonry are recent examples of buildings, but they have suffered extensive damage. But they were in the proximity of the epicenter. But other recent buildings were much less damaged.
And also, if I might add something here, the most recent, or as I showed, the RC frames with shear walls would be more near Marrakech, so a bit further away from the epicenter. So we did not really go and observe in details those buildings, but from what we could see, that there was not heavy damage on those buildings.
Yeah, because it followed the codes generally. That's why we didn't observe really damages around Marrakech, even if, as Afifa said, the acceleration in Marrakech was higher than what it is in the code. We did really not notice lots of damages on the recent building in Marrakech.
Thank you. Then I see one question about, some general information about the webinar. We did record the webinar and it will be available on our website in the following days, I think, or in our YouTube channel. And also, the report you already said it will also be available on our website soon. Then I think, if I'm not wrong, there's one more question that we haven't addressed, which is about the reconstruction. Are there already technical documentations with recommendations for the reconstruction, for self-construction in particular? And how the local population view the reconstruction from a technical point of view? I don't know if maybe Hamza, you want to?
Yeah, maybe. Actually, the recommendations for the reconstruction are the same that are in the code RPS and RPCT. So the recommendations are quite good on the code, and we just have to follow this recommendation. Yeah.
And maybe, yeah, do you think they're or for the self-construction? Is that, do you think that?
Yeah, it's made also for self-constructions, because in the RPCT, it's really simple, and we don't have to be engineered to really understand what it is inside. So it's also made for non-engineer.
Perfect, thank you. Then I think there's one more that Savvas you're about to answer, but I think we can also take it here. So if you noticed a different systematic use of wooden chaining elements in the adobe structures.
Yes, thanks for the question. In general, we didn't observe any chaining elements in both stone or rammed earth and adobe structures, in earthen structures. So these were completely absent in all the rural areas that we visited. We just showed a singular case where it could be a chaining element.
Okay. Thank you very much. If I'm not wrong, I think we addressed all of the questions, or if anyone else has a question, I think now is the moment, like, to either write in the chat. You can also raise your hand. Otherwise, I'd say, there were a lot of, sorry, I kind of, I just sort of thanked some of the many people saying thank you for the great presentation. I tried to move you to the answered section to filter out the questions to make sure that we don't miss any. But yeah, thank you. Thanks everyone again. Especially our wonderful team, obviously, for preparing the great presentation, and it was really interesting, I think. and everyone for attending. So yeah, it's nice to see the interest in this mission. Thank you all for your questions also. And as we said, so the report and video will be, I mean, the video probably a bit quicker than the report will be available soon on the website. And I think if you have further questions, you can also contact our team members, maybe directly, or someone at SGEB, and we transfer the question. And I think, I mean, yeah, as we said, especially, I think we have to pass a big thank you again to you, Hamza, for organizing everything so well, and obviously to everyone else for taking the time to participate in the mission and preparing all the wonderful documentation. I think it's a lot of work. And then also to all the people, obviously, in Morocco, I mean, at UMC, but also, as you mentioned already, Hamza, in the villages, the ambassadors, all the authorities that really helped and were really supportive of the mission. The EPFL Alumni Network, Catherine Bayer, who helped a little bit with the presentation, so, or I mean, the preparation, I should say. And I think that would probably be it. I think in maybe one more announcement in terms of SGEB. So we have the next webinar already in 2 weeks, sort of a Swiss lunchtime seminar. Swiss in the sense that it's at noon Swiss Central European time. On the 14th of March about vibrations in buildings. Especially I think in industrial buildings. So you are all welcome to join that. It will be a German seminar. And there's nothing else. I think a round of applause for our presenters, and have a good day, everyone.
Thank you.
Thank you.